descriptive statistics out of the way, we are now on our way to looking at how you can explore any data that you may have been given. We are very used to tabular data, which means data which is organized as rows and columns, pretty much as in a spreadsheet. In fact, that kind of data is the most common kind of data we will run into, and much of the analysis that we will do going forward will be focused on tabular data. So we will spend a fair bit of time looking at tabular data. But there is one more concept I wanted to introduce and make sure that we have some conceptual understanding of that. And that is about arrays. So arrays are collections of numbers. That is the format in which data is often represented for advanced analytics, for natural language processing, for deep learning, for machine learning algorithms, and so on. So it is important that we have some understanding of what data arrays are and how they are structured. So with that, let us switch to the slides. As I mentioned, an array is a collection of numbers, and this collection is organized along dimensions. And arrays are therefore n-dimensional collections of numbers, where n can be any number. So tabular data of the kind that we would find in a spreadsheet would be a two-dimensional array. Now consider an array here. So this is a collection of 5 numbers organized together, and they are grouped together, as we can see, uh, enclosed in these square brackets. So what do these numbers mean? They normally have a structure, which means their particular location in a particular spot in this array has a certain meaning. So, for example, this could represent characteristics of a house in a particular city. So, 5, for example, could be the number of bedrooms, and we can write that here. This could be the number of garage spaces. This could be, for example, the distance to the high school, and so on. And this could be for house number 1. Now imagine we have another house and we get the same characteristics for that house as well. And all of a sudden, now we have 2 arrays because there's one array for each of the 2 houses. And maybe we are doing this analysis for several homes in a neighborhood, and we have multiple homes. And so we have 6 homes, and we have all of their characteristics organized in 6 arrays. But they don't need to stay as 6 arrays. They can all be combined together as one single array. For example, we could put like one big square bracket here, another big square bracket here, and all of these little square brackets inside could be part of this one array. And then we have a two-dimensional array, because whereas our initial array had just one row and 5 different columns, now uh, we have 5 different columns but 6 different rows. So we now have a two-dimensional array which is of the size, or which is of the shape, uh, 6 by 5. So 6 rows by 5 columns. This is the convention it is written in. 6 and 5 are also called the axis of this array. Now imagine this array represents homes in a suburb of New York. Imagine we had the same data for another suburb, say for a different city, say Boston. Now we have 2 arrays again, both of the same size. Does it mean that they need to stay separate? Can we combine them just like we did previously when we had single homes in a single array? Yeah, we can. And we don't have to put it at the bottom, because then we'll have to know where do we, where does one city stop and the other begin. We can actually stack them one behind the other in a three-dimensional format. So this becomes a three-dimensional array which has a different axis for representing the city that the data relates to. So we have now been able to organize our data in a very concise and compact way in a single container, which is what this array represents. In fact, we don't have to stop at 2. This particular array now has the size 2, 6, 5, and let's look at what this represents. So 6 and 5 are the rows and columns here that we initially saw, and then there are two of these. So that means this array has the shape 2 comma 6 comma 5. So there are 6 rows, 5 columns, and two of such collections, and that is what this means. We could have more uh, things at the back, so we could have yet another city's information that we could pack behind. And now this array becomes an array of the shape 3, 6, 5 because there are 3 of the third dimension. In fact, there is no theoretical limit to the number of dimensions you can have in an array. However, you cannot represent more than 3 dimensions in any way which can be visualized by us as humans because we live in a 3 dimensional world and our brain can only perceive 3 dimensions. We could have 4 dimensional, 5 dimensional, and additional dimensions as well. Um, in fact, the way I like to think about it in my head when I look at a 4 dimensional array is that this 3 dimensional array that you see on screen, this is like a Rubik's Cube. And if you had multiple Rubik's Cubes hanging along a wire, one after the other, then that wire would represent the fourth dimension. And then you could hang all of these Rubik's Cubes in another sort of a key ring that is the fifth dimension. And that somehow, I internalize the concept of dimensions beyond 3. But anyway, that is less important. What is really important to know is that arrays are compact representations of data. They have dimensions, and every number in an array exists at the intersection of all of its dimensions. So, for example, if we were to look at uh, this number here, 6, this exists at in the second column, in the first row, and in the second part of the third dimension. So this is sitting at the intersection of the 3 dimensions as 2 at 2, 1, and 2. So that is what I wanted to point out about arrays in real life. I can give some examples of multidimensional data that is expressed as arrays, that is stored as arrays, and will come to you as arrays. So color images, for example, will have 3 dimensions. Uh, one, the third dimension will encapsulate the color, R, G, and B. So there'll be 3 of those in the third dimension. And videos will have 4 dimensions because the fourth dimension will be the time dimension for each of the frames. Arrays are important because that is how data is organized for complex operations and for more advanced analytics. And they also allow for very efficient compute because you don't have to go through every number one by one. You can perform what are called vectorized operations, which are far more efficient than loops or other computational techniques. And that's really what I wanted to share about arrays. Now, tabular data. Tabular data is the most familiar form of data that we have. It's really just a table. It has rows and it has columns. So in a way, it is a two-dimensional array. The difference between tabular data of the kind that you would find in most statistical software, including in Python, which is what we will be using for the coding sections of this course, is the fact that in an array, the dimensions don't have names. You have to keep a separate record of the names for the rows and columns. Whereas most tabular data, for example, represented as data frames, would have names for the columns and the rows. And that makes it extremely easy for us as humans to use them and improves the usability. So very similar to what we would see in a spreadsheet. So arrays, again, our trusted diamonds data set, where we have 50,000 plus diamonds, and what you see here on screen is the first 8 elements. And the items in bold here on the left, this part, these are the row labels, and these are the column names. So everything exists at the every data point, every value exists at the intersection of each of the dimensions. So for example, this 56.9 is for diamond number 2 and the data attribute depth. Why does this start with a 0? Now that's a quirk of the programming language Python. It doesn't have to start with a 0. In R, it would have started with a 1. But that is, again, it's a trivial thing. Uh, but just in case the thought occurs to you, I just wanted to make sure you understand why this one, the first item starts with a 0. And here is the same data represented in our familiar and trusted Excel spreadsheet, very similar to what we just talked about. Now, data in tabular form is laid out as a two-dimensional matrix, whether as a spreadsheet in R, Python, Spark, you name it, and or in a database table as well. Rows generally represent individual observations, whereas the columns are the fields or the variables, and they are also called features, which is interesting because if you are thinking about machine learning and AI, and if someone says the word features, that's what they mean. These are the fields or the variables in the data. We covered this before. Variables can be numeric or categorical, and categorical variables can, in addition, be ordinal as well. Or they could be cardinal, which means that there is no order between uh, of any sort between the categories. Numerical variables, again, they can be of different types as well. Often this distinction doesn't matter too much to us. So they can be integers, which means they are whole numbers, they don't have any decimals, or they could be floats, which is just a technical term for a number that can have decimal places. And they're continuous, which means they can take any value. So things such as height, income, they could take within the range, they could take any value. It could be a 2.69 or 2.693. There is no limitation to what value they can take. And categorical variables, as I mentioned, they may be cardinal, for example, species, gender, names of countries, etc. Or they could be ordinal, which means there is a natural order to the different items in the variable. So, for example, low, medium, and high, there is a certain order to it. Or, as an example that was provided in the previous video, the level of education, there is a certain order to that as well. In some statistical software, categorical variables are also called factors, and they have what are called levels. Individual values are called levels. And finally, another thing I wanted to mention was that most advanced analytics, algorithms, machine learning, AI, deep learning, they require all categorical variables to be converted to numbers. They cannot consume text data. Everything has to be in numbers. And when we get to those sections, we will cover how we convert categorical data to numbers. Now, tabular data can come to us in many forms, and most software, most analytical software, whether it's Python or databases, they can read most of these with relative ease. There are connectors available, and you can read just about anything. In fact, for example, the pandas library in Python can read just about any data format you can throw at it. And here are some examples of what it can do. It can read comma separated files. This is the most common format in which data is shared, and this is the most common format that you will find data in. Then there can be tab separated files, fixed width files, and so on. And you can read all of them quite easily in uh, Python, in Excel, in SAS, in R, you name it. And most of those things have connectors built in to read data. So that's generally not an issue. Finally, very often we have to try out different things. We have to try functions, we have to see what we can do with data, and we have to practice, we have to experiment, we have to demonstrate a particular point, and for that we need data. Most analytical software comes pre-packaged with some toy data sets, and these can be accessed for experimentation of the kind I just described. Even though these are toy data sets, some of them are actually quite extensive and very large. Some of them are actually larger than real life data sets that you would run into. The diamonds data set that we have been making an example of is a toy data set, but it has data for 53,000 diamonds. That's not a very small data set. Then there are additional data sets that are extremely large, and they are so large that they cannot be even be stored in memory. And these data sets relate to text information that may have been gleaned from services such as Twitter, Facebook, or product reviews, which can create a lot of data. So during this course, we will limit ourselves to such data sets or to publicly available open source data sets to explore and explain analytical concepts, ideas, algorithms, and tooling. And just wanted to mention that one final thing which is quite interesting is that it is also possible to generate your own synthetic numerical data within most software. Within Python, there is a function that you can use to create synthetic data or artificial data with defined parameters relating to mean, standard deviation, correlations, etc., in order to test out any algorithm or anything else that you might be trying to do. And there is no limitation to how many rows you can create, how much data you can create there. You can create millions of rows within a matter of seconds or even less. Next, just a quick reminder on the diamonds dataset. We had a quick introduction to the diamonds dataset in the previous video. So there are over 50,000 diamonds in this dataset, and there are several attributes relating to data to each diamond that are available in the dataset. On the right hand side on the slide, you see uh, the actual data represented in a spreadsheet. On the left is the data dictionary, which explains as to what each of the different columns are about, what kind of information do they contain. We will be using this data set very often as part of this course. So what are we looking for when we are doing exploratory data analysis? You have a bunch of data that has come to you and you have to go and explore it. So what does that actually mean? So the possible inquiries that you might like to conduct include several. So for example, the first thing you would like to do is you would like to know how much data do you have? How many rows are there in the data? Because generally the way the data is organized is that every row is a single observation. So you want to know how many data points do you have, and that is given to you by the number of rows. You also would like to know how many columns do you have, or how many fields or variables or features do you have in the data set. And that is again something interesting. And both of these things, the number of rows and the number of columns in tabular data, you get they're also uh, referred to as the shape of the data set. So uh, by asking for the shape of the data set, you get an understanding of how many rows it has and how many columns. Then you want to find out what kind of data exists in the different rows and columns, which appear to be numeric. Are there dates? Are there strings? Is there just plain free-form text? What is going on? You would like to see that. You also want to see the names of the different columns. And do the names tell you something? Sometimes the names of the columns are pretty descriptive, and when you read it, you know exactly what it would contain. So if a column has a title called age, then you know exactly what it is. You would also like to do a visual review of a sample of the data set. Just show me 10 records out of the millions that might be there. I would just want to get a feel for what things look like out there. So that is what a visual review would help you get. You also want to look at the completeness of the data set. Are there missing values or columns that appear to be largely empty? So the column is there but doesn't seem to contain much data because there are many blanks. And for columns that are categorical that contain text, you want to know how many unique values are there. Like if it is a listing of states, then are there 50 states, 20, 10, or more than that? You would like to know that. And how many observations are contained in each category. So that's also another thing you might like to know. For numerical columns, you would be interested in finding out the range of values. What's the minimum? What is the maximum? And you might even be interested in some descriptive stats here for numerical columns. You might like to know what the standard deviation is. You might also like to see the distribution for the different columns. Just where are the values sitting? Like what ranges have the most values and what is the shape of a histogram like? So that would be useful as well. And finally, you might like to interrogate the data for correlations. This is really important because if the data is highly correlated, that means many of the different columns are really just proxies for each other. When correlations between different columns or different fields are low, that means each individual column or each field contains a lot of information that cannot be found in other columns. So that is also something interesting you are interested in knowing about. So let's look at practical examples of some of these questions that would occur to us as we analyze data. So how much data do we have? How many rows in my data set? And here are two examples from analytical software, and I call Excel to be an analytical software as well because it's an extremely powerful piece of software that is used every day by millions of people across the world to perform data analysis. So in Excel, for example, you would see at the bottom, you see the count, and you get to see the count when you select a certain range of cells. So here we have selected column A in its entirety, and that tells us that there are 53,941 rows in our data. Know that this is one more than what we would expect at 53,940. That's because the count includes the header, which is caret, which is here. In the same way, when I look at information in Python, I can see the shape of my data there, 53,940 rows. It actually also tells me how many columns I have, which is good. And that is going to be my next inquiry. What is the number of columns in my data set? In Excel, this time I have selected the entire column and it gives me at the bottom, I can see there are 10 columns and I get the same thing here in Python as well. So the next thing that comes to our mind is what do these different columns mean? And normally to answer that question, we have to ask for the data dictionary. Sometimes we might think that just by reading the name of the column, we know everything that we need to know, but that often may not be true. So when we see the price column, we assume that the price is in US dollars, but it could have well been in another currency. It could have been in euros or something else. So it is always good. It's a good idea to ask for the data dictionary or make sure that we have a correct understanding of what each of the columns contain. We can examine the data visually to be able to see what kind of information is contained in each column, whether it is numerical, cardinal, ordinal, and it gives us some idea of what things are like. Most software will actually do this analysis for us and it will tell us what kind of data is contained in each column. So here, for example, in Python, we are able to look at information behind different columns and my column names are listed here. And here I can see what kind of data is contained in each. So float 64, as we mentioned earlier, that's just a number. And these are categories. This is again numbers. This is an integer. and we can see what kind of data types exist. As I mentioned, the names of the columns sometimes can tell us a lot about the data in them, but it is always good to ask for the data dictionary to get an understanding of what they actually contain. In the case of the diamonds data set, which appears to the right, yes, we can make reasonably educated guesses as to what the columns contain, but in some other cases, we may not be able to do that. So if you see the example on the left hand side, that is an extract of data from the Applied Climate Information System, and it has column names. Well, we can sort of guess it, and if we have the right contextual knowledge, we may be able to intelligently figure out what those things mean. For example, county is represented as a number. And for those who have worked with GIS systems or are generally aware of how counties in the United States are organized, they would know that every county has a standardized FIPS number. And because this is a 5 digit number, it probably is that. And that is an accurate guess. But not everyone may be able to know that. AVGT, now we can imagine that this is climate data, so probably this means average temperature. Maybe the next field is minimum temperature, the next one is maximum temperature, and so on. But we don't know, what does HDD mean? And HDD actually, if you look at the data dictionary, it means heating degree days, which is the number of days when the temperature in the county was below 65 degrees, which is the temperature at which it is considered necessary to turn on heating. Similarly, GDD stands for growing degree days. These are interpretations that we cannot work out just based on common sense. We need the data dictionary. So I cannot overemphasize the need to ask for a proper data dictionary from a person knowledgeable about the data and make sure that we have that before we perform any analysis or draw any conclusions on the data. A visual review of the sample of the data set. So here is a data set which includes information on about 20,000 homes. And of course, on screen, we can only see a handful. But these are 20,000 homes in California sometime around 1990. And MED-V, which is the first column here, this one here, is the median value of the house in hundreds of thousands of dollars. And then there are all of these other variables that are available to us relating to those homes. How many bedrooms, what's the population of the town that that house is located in, etc. So we have all of this information. And the visual review tells us that the data looks pretty complete. If we had drawn a random sample and we see that everything seems to be filled in, things look good. So this gives us a sense in a human sort of a way, just by visual inspection and examination. I would encourage you always do that. Always helpful. The other thing to look for is how complete is our data. Are missing values obvious? And sometimes they may be, and sometimes they may not. Sometimes missing values may appear as just blank cells in the data. Some other times they may appear as NaN entries, which means not a number. Sometimes they will actually just be text denoted as missing or something like that. So missing data can come in many different forms. And why this is important is if you see missing data in your data set, then you would like to know how much as a proportion of a particular column or a row's values are missing, because that will help you make a judgment on the usability of the data. If a lot of the data is missing, then your data set may not be usable, or you may have to apply uh, special techniques to fill in the data or impute the data in some way to make it useful for your purpose. So again, that is something to think about as we do an exploration of our data set. Finally, missing values. As I mentioned, missing values in software are often called nulls or nans or none. They may also appear as just plain English missing or NAs or some other text, which the machine may not interpret as missing, but we as humans would know that that is how missing data is identified in our data set. What you see here is uh, an extract from Python uh, information on a data set. And what you see here is that for every one of the columns, we are able to see how many non-null values are there. So it looks like, based upon this, most of our data is complete because there is no column here which has anything less than 53,940 non-null values. So it allows us uh, to find out the extent of missing values. So in other words, the point of this slide is to say that you can use software to find out how many missing values are there in your data set. Continuing on, we would also be interested in the distributions of our data. So for example, in our diamonds data set where we have all these different cuts, ideal, premium, good, very good, and fair, we can construct a histogram fairly easily to see how the data is distributed across different categories. For numerical variables, we can actually get a histogram, which means it is a continuous histogram. And we can see, for example, one interesting one to look at here is the price, the graphic for price. And we see that most of the diamonds are lower in value, and there are a few that are higher in value. So it is sort of a very long-tailed distribution which skews down to the right. Correlations, we covered this in the previous video as well. You would like to look at correlations, what is going on here in terms of relationships between different variables. And I can see that clearly there is a very strong relationship between carat and price. So the heavier my diamond, the more expensive it is. Uh, and that is also borne out here in the Pearson correlation coefficient. My carat and my price have a high correlation very close to 1. So that means things are driven very strongly by the weight. And I can also see my weight is very highly correlated to the dimensions of my um, diamonds, which means that larger dimensions make for a heavier diamond, and that is of course common sense. Finally, nearly all analytical software will give you basic descriptive statistics for any data that you can throw at it. So for example, this is a table of the mean, the standard deviation, the minimum values, the different quartiles, the maximum values for every one of my numerical uh, values in the diamonds data set. And to generate a table like this is generally extremely trivial in most software. And that is because this kind of work has to be done by everyone for just about every data set. We can also calculate individual uh, descriptive statistics for each of our columns, and there are functions that are built into most statistical software to do that. So if you have a data set, you can ask for all of these things from your team or your analyst, or you could perform the analysis yourself, as we will see in the coding section in the coding video for this course. We can also, as part of our exploration, we can sort the data to look at the top values. We can list out the unique values for uh, our categorical variables. And we can take a random sample of the data for review and examination as well, just like we did before. Finally, we talked about graphing the data. We can do histograms and bar charts. The ones that you see on screen are very simple ones. We'll see some others as part of the next video, which is on visualization. We can use scatter plots to examine the relationship between two variables, and much of this is going to be covered in the next video. The next item we are going to cover is going to be split, apply, combine, which is essentially uh, a set of operations that would be very familiar to people who have worked with pivot tables. But let's cover it in the next video. And thank you for watching, and look forward to seeing you again on the next one.